It's a great pleasure to have Yuri Boykov here. Some of you know Yuri, some of you most likely do not. So let me tell you just a little bit about Yuri. He is at the University of Waterloo right now. He's an affiliate faculty member at the Becker Institute. He was at the University of Western Ontario until just a couple of years ago or a year ago when he moved to the University of Waterloo. Is that right?
Mm-hmm.
And Yuri did his undergraduate degree, I believe, in physics on the other side of the pond in Moscow. Is that right? He has a PhD from Cornell University in operations research optimization. He's done really outstanding work, really truly outstanding work in computer vision and medical image analysis, with working on a wide variety of problems, including stereo, motion, segmentation, image restoration, you name it, all sorts of low-level vision problems as well as some recognition problems. He is best known for work that he did in the late 90s, in particular with Olga Wexler and Raman Zabi on Markov random field energy minimization using graph cuts. And that is work for which he also won the Helmholtz Prize, which is one of the two most prestigious prizes in computer vision. He won the Helmholtz Prize in 2011, if I got that right. And so it's a great pleasure to have him here today, and he's going to talk about stuff. Segmentation.
Yeah.
So take it away.
Well, thanks, David, for a very generous introduction. So it's a pleasure to be here and present some of my work. So some of that, in fact, big chunk of it will be a review of stuff that I've done over the years, and the list of co-authors here is far from comprehensive. So these are my colleagues and my students and postdocs, but not everybody's here. All right, so segmentation without full supervision. And let me just give a little motivation for my talk. So segmentation problems range from how simple or how complicated they could be. And the most simple example you see, I can imagine, would be something like this. It's from a robot soccer competition where the image is made to look easy, where objects have unique colors. So basically you have linearly separable features to begin with. So you have colors that can be separated by thresholding. So that's really too easy. Well, and of course it's very far from general images where objects may have fairly complicated appearances that hard to separate linearly. But this is where, well, let's say you have all these deep learning things, and if you have fully labeled ground truth, nowadays you can learn features, like the network will learn some embedding with features which linearly separate the objects. So you basically, instead of having them on the input, the network learns how to embed the images in a way that features are separated. But in this case, you have to do a lot of manual labor to generate those fully annotated pixel-accurate masks in order to achieve this. And this is too much work. You may say, well, maybe it's worth doing it once, and then you solve computer vision, learn all the features that there is. But there is kind of a question here. Is it worth it from that point of view? Do you really learn everything there is? So for example, do networks learn about geometry, shape, or any of the other high-level properties that we're interested in? There are doubts about this. So basically, I mean, there's maybe lots of other things you can say, but this is an example from a recent paper that's about to appear in ICLR, where it seems like the recognition, at least in the context of computer vision, is basically primarily focused on texture. So you have like a texture of an elephant, shape of a cat, but it picks up primarily on the texture. So I'm not saying a definitive answer, and I'm speculating because no one really knows, but I allow myself to speculate, to say that it's probably a lot of it is just about picking up appearance model and texture. Highly hierarchical way of representing it, and very successful for many tasks, but I don't think that we'll learn any of this. That's speculation, of course. All right, so, and then just want to say that my impression is that success of it in segmentation, and maybe even in object recognition, is primarily in picking up those appearance models, textures. It's a speculation. But I just want to remind you that before the deep learning, people also worked on appearance models for sure. But even more so, the focus was because the appearance models we had were crappy. in the old days. So this is definitely where you get lots of leverage nowadays. But we did learn, because of the appearance models were weak, we really focused a lot research on picking up geometry, shape, topology, and all those high-level properties, and somehow representing them through various objective functions and optimizing them. So it would be great to combine this, because you do want, besides the appearance model, have something else. And I'm not saying that I know how to do it. I'll just say this is a general thing. It would be nice if we were able to combine some kind of representation from here with high-level geometry, shape, or whatever that we get there. And why would you want to do so? Well, perhaps that's what's lacking when you have this overfitting problems that you know, or domain adaptation issues. Maybe that'll help. But in the the context of my talk, I will primarily focus on simplifying the training process. So I'll try to make it simpler so it wouldn't require as much work as you see it's required right now. So that's the focus of my talk, and the outline, there will be two parts. Actually, the bigger part would be a more review of non-deep work, and in part I allow myself to do so because I expect that not everybody, particularly the younger part of the audience, wouldn't necessarily know a lot about this. But there will connect, like the last third of the talk will be about how that stuff is helpful for deep learning as well. So basically, first I'll talk about objective functions in a shallow context. And when I say shallow, I mean non-deep. That before deep, okay? That's not my term, but I totally like that term to divide the two. And then you will see how similar objective functions, in a completely shallow sense, go and become very helpful as loss functions in the context of deep segmentation. Okay, so shallow segmentation part. And by the way, I also want to say that this part of the talk will be a little deeper technically. This will be shallower. So the shallow segmentation will be deeper technically. The deeper segmentation will be shallower technically. I like to say that. Okay, anyway. So let's start from the shallow world. And the thing is, this slide is supposed to scare you because I'm saying how you segment depends a lot on how you represent your segmentation. And there's lots of models people developed over the years. This is not all of them, but I'll just focus on one of them throughout the whole talk. It's, first of all, that's where I worked a lot on, that's my comfort zone. Also because that fits well into later deep framework, because we're going to be labeling discrete points. I'll start with labels being associated with the nodes, and you can think about them for now as integer labels, like category or something. For a smooth start, I'll start with binary, just two labels. And let me give you an example of the simplest shallow regularized or graphical model that people used for years, and it's not like Giman may be the first one to introduce it or something like this. So this is a model that penalizes your segmentation based on the number of discontinuities between neighboring points. And well, you can write it down like this. So if you have this neighborhood system and you go over the edges on this graph, and if two neighboring labels are distinct, you pay penalty W. So overall, you can think of that as also as a length of the boundary. So you pay for the length of the boundary, and you can formally convert from like counting the number of discontinuities, penalizing them, into geometric objective. You can say this approximation of geometric length for this segmentation. But the question I'd like to ask is to why do we need those graphical models? So what do they give us? Even this simplistic example needs explanation. Why do we need this? Let me give you the simple example to get the gist of what the shallow segmentation is about. So this is a toy example. I want to extract this object from the background. And for now, I make a very simplistic assumption that I know color models, the distributions of colors in the desired object and the background. So these two distributions of, say, intensities or colors, this is your feature domain. So the simplest thing you can do, and in this case, I'm suggestive that perhaps linearly separable means I can separate them based on just thresholding around here. So, but if we take it a little bit more scientifically, well, let's compute the log likelihood ratio at every point. What do I mean by this? Well, if you take a specific point, pixel, well, it will be some value here, and then you have two likelihoods for how that intensity fits the object and how well this intensity fits background. You compute the ratio of the two, take negative log. So this is negative log likelihood ratio for this two decisions, object or background. And I can actually display these as scalars. At each point, it's a number. I can display them as an image itself because I'm showing the value using MATLAB color code. Blue means negative, red means positive, and anything in between. So it's real values, of course. But you can see that in this simple case where, well, it's very simplistic and probably inseparable, you can all see it here. So if you just threshold those log likelihoods around 0, you're going to get this segmentation. This is our first segmentation of the day. And it's just based on pixels which have high likelihood to belong to the object, which means they're here below this threshold. They are highlighted, and those which are more likely to belong to the background, they're removed. But now, instead of showing this as log likelihood ratio, I want to show this as an optimization problem because I'm moving towards optimization. How you convert this log likelihood ratio test to optimization? Very easy. So I'm just summing over all points. These are my variables at each pixel, 0, 1. I have to decide whether 0 means background, 1 means foreground. And these are those scalars. So I'm just like it's a dot product between those and the vector of segmentation variables. And why is this an optimal solution for that? Well, it's very easy. It's an objective where you can optimize it individually over the pixels. And then notice that if FP is negative, then you would choose SP to be 1, because that reduces the value of the objective. And if FP is positive, you would choose 0. And that would overall give you the lowest possible value of the objective. So it's very easy optimization. It's a linear objective function, so you can write it as an optimization, or in fact, it's just log likelihood ratio test. But the reason I formulated this as an objective function, because it's not enough. This is where you get this kind of artifact because of the noise. Like it's not entirely linear separable, there is overlap. So here's where we can bring our pairwise graphical model that penalizes discontinuity. So this is the most simple kind of regularization energy. So you combine those log likelihoods with some kind of idea of simplest shape prior you can imagine, and then you can optimize those for certain kinds of regularizers like this. And pairwise regularizer you've seen on the previous page is easy. So basically what you see here is a basic example of typical shallow segmentation regularization objectives, where some kind of appearance model, in this case linear, simplistic, combined with some kind of shape prior, you can formulate this in MRF setting. There are lots of ways you can come to this story. I gave you the most kind of down-to-earth way to get there. So there are, of course, extensions. I mean, this is where it starts. You can think about this as a most basic example. You can think about this as a quadratic term, because it's pairwise objective. You can go to high-order geometric constraint, and that's what a lot of research was focused on, how to represent high-order properties. And that could be curvature, convexity of the shape, or topology of the shape, or lots of other properties. And this is kind of general work. Objective functions get progressively harder and harder to optimize. Okay, well, let's stop that direction. Let's look a little bit more at the appearance model. So in the way I formulated it with, if you have the known color models, then this is just a linear objective. But I'd like to massage it a little bit to get to my next point. So all I did in this in this linear thing you showed in the previous slide, I turned the ratio, log of the ratio of two likelihoods into the difference between two likelihoods. That's all I did. I plugged it in back in there, and then you see this is that difference. But I added the constant. So, but I now wrote this energy, exactly the same energy as before, in the form where you can see the first term sums likelihoods of the object over pixels assigned to the object. And this term sums likelihoods of the background model over pixels assigned to the background. So it's a sum of log likelihoods. It's like I can write it down as this, and the only reason I started from log likelihood ratio, I wanted to connect something really trivial. And also, if I wrote this and told you this is linear, you may have had more questions. Like I just kind of went through more trivial phases, but this is in case where the models themselves, theta 1 and theta 0, the distributions are known. This is just a linear model. But this is where you can get to much more interesting. Suppose now you don't know the models. So remember, I made this assumption the models are known. If they're not known, you can treat those theta 1 and theta 0 as additional variables, and all of a sudden your problem turns into high-order objective. So now it's actually, I'm supposed to have a formula here. something messed up. So it's the same formula, but like if this is also, like not just SPs, but also the thetas are known, this is a high-order objective, harder to optimize. And that's actually turns out to be, like in this formulation, joint model estimation and some kind of shape regularization or some other regularization on the right-hand side. In other words, you see an example on the left-hand side, something that you can think of as parametric clustering. This is k-means, well, you should have some like likelihoods, plus some shape properties on the image domain. So let me give you the most trivial example so that you believe me better. Well, let's take the simple example where you can imagine, even though I don't know the models of, let's say, white matter, gray matter in the background, but you can imagine they could be described by Gaussians. Like there is one Gaussian distribution for bright color and plus or minus so the gray matter and background. So there are three models. We don't know the models exactly. We know the class of the model. We know it's, let's say, it's a Gaussian distribution. But we don't know the theta. Like in this case, the parameter of mean is not known. So if I plug this with unknown theta into my sum of log likelihoods, you're going to get k-means exactly. Because like the negative log of this gives you what's on the top. So the sum of log likelihoods you've seen before is just the k-means in the color space, in the feature, in this case, just intensity domain. And you combine this with some kind of regularity in the image domain. That's what this energy is about. And this is a well-known Chan and Bessey model, 2001. It's exactly fitting Gaussians or parametric clustering, if you want to, in the feature domain, plus some kind of shape properties in the image domain. Well, if once we get to errors like this ones, well, I can do them not in a color space, but let's say in the, suppose these are features in 3D after you map, like noisy features in 3D by matching shifts in two viewpoints. So, and then you can just try to fit planes there, but regularize the boundaries in the image domain. You can get something like that going. But the question that you immediately may ask, so this is still very simplistic, we're assuming that each cluster, if you like, each unknown cluster, we're doing unsupervised clustering here, unsupervised segmentation, well, is defined by Gaussian. It's not realistic. Like even in this example, like zebra is already two modes. You cannot describe it by one Gaussian. So, and then for this, people propose, well, don't use those simplistic models, but maybe, well, maybe Gaussian mixture of Gaussian. So each object may be described by two modes, three modes, and you will be starting to fit more complex models. So that's well-known region competition. I mean, well-known at the time. I don't know if people know about this anymore, but you've heard about this. Okay, so good. But I mean, the idea here is like you allow more complex models, but it becomes more, I mean, k-means is an hard problem if you want to find a global optimum for it. Well, this is already even beyond that because you're fitting either Gaussian mixtures to each cluster, which itself is a complex problem. But also, okay, another way you can think about like theta I, your descriptor for the model could be like even the histogram. So it could be very high dimensional model fitting. But it can capture this. And think about this. This is actually what this regularizer tells these two modes to unite. For example, that's why it's optimal, because there are too many discontinuities if you don't put them together, but together, these two modes may work. This is kind of the gist of this idea. Well, in the context of binary segmentation, this idea was popularized in the context of graph cut. So how many people heard graph cut? More. It's the same thing. It's a binary version of it, and there's an interface on top of it, because, well, now you're talking just about object background, and your initial model is described by from the box and not outside the box. Otherwise, it's exactly region competition from Yuri. And okay, the regularizer here is graph cuts, while like Yuri, I think they use level sets at the time or something like this, but the model itself is the same. Okay, so basically, the advantage here is you can try now fit arbitrarily complex histogram. You may wonder though, what does it mean fitting histograms from any kind of intuitive point of view? Because like when you fit Gaussians, you see what's going on fitting histograms. See, histograms can fit to anything. Actually, there is a way to interpret the sum of log likelihoods, like here or here, doesn't matter. You can actually formulate this as entropy clustering. You can prove that, like for k-means, for basic k-means, you know it's variance clustering. You're finding clusters with low variance each. That's what you mean by the sum of errors, right? While for this more general version, which by the way called probabilistic k-means, that's not my term. Andrew and G had a paper at UAI like maybe 10 years ago where they coined this term for this type of model fitting, where your models are pretty general. So it's called probabilistic k-means. But in any case, I lost my thought of train thought. Where was I? Okay, yeah. So you can think about this as histogram. Sorry, not histogram. Entropy clustering. You're finding clusters where each cluster has as low entropy as possible. So you can justify this. But numerically, it's very sensitive. Like you're fitting histograms straight. If you remove a regularizer from here and just try to fit histograms, you're going to converge in one step. In one step, your histogram will all fit whatever you started from, and you're not going to move anywhere. So I'm just pointing that numerically speaking, this is actually not easy. You can imagine k-means as hard, actually, if you do it right. I mean, hard meaning like guarantee anything. For this, it's much harder to guarantee anything. And actually, you have to be very careful numerically. Like, for example, you have to control build size. If you go to high dimensions, for example, now suppose your feature is not RGB, but suppose you also add like some motion or depth. This idea gets stuck in local minima, even though it's impossible to make it run, histogram fitting. But that's actually what motivated us to propose, like people don't do clustering like this in the learning community. I mean, many of you probably from the learning community. I'll be surprised if someone raise hands and tell me that this is how you do clustering. Well, at least people more familiar, probably more comfortable with doing kernel clustering instead. At least it's well, more scalable to the feature dimensions. And that's one of the extensions we worked on relatively recently. So it's kind of, instead of entropy clustering, it's just directly any of your favorite kernel clustering objectives. It could be normalized cut objective, it could be kernel k-means objective, and all you need to define is pairwise affinities between the points, and it doesn't matter what the dimension is, so you can get much more stable results. Well, it's kind of more recent work, but at this point, okay, for example, we have it working on video, and I'm surprised that my video was embedded in the presentation, and I moved my slides to a different computer and it's still there. So completely unsupervised segmentation, no deep learning, okay? Just features where clustering is colors, and this motion field obtained from whatever optical flow, or I mean, you have a sensor. Okay, so that's let's say some of the kind of overview of shallow segmentation before deep learning. I just want to say that these objectives could be derived and motivated from totally different perspectives. So I started from, and I went through all of those phases, different points of my life, I suppose. So started from MRF, and you can think about them as log likelihoods plus logs of priors. You can go through geometric perspective and think about those as geometric objectives. Information theory, I love this. This is very good and give you lots of insights. In particular, you can motivate sparsity objectives this way in a very nice way. But also, like, there is a most maybe down-to-earth perspective. It's just optimization of set functions. So how you derive exactly this energy is your own business. But once you, let's say, write down your energy as a sum of what we call factors. Like this could be pair array factors, meaning a factor could be a pair of neighboring points, so it could be higher order clique. Well, you can write down those energies as sum of factors, and depending on how complex your factors, you talk about optimization. Yep.
I mean, isn't that a bit too general, though? I mean, that doesn't really give you a way to solve anything, right? It's just
yeah, I have a few slides kind of continuing this line of thought, and maybe we can come back to like I'm just trying to keep track of time also because I don't see any clock, and I have to be careful. Okay, I have my laptop, my cell phone for this. So let me give you a few slides on this perspective. I just want to highlight it more than others. So good question. So where did it all start? I mean, actually, what are set functions? So I mean, you have a set and subset of it with a subset of it in a union intersection operation. So it's a lattice of sets. And well, set function is basically a mapping from the power set to real numbers. From any subset to real, for any subset, it gives you a real number. We can think about this as an objective function. In the context of segmentation, it's directly relevant. Because for me, omega is a set of pixels, and a segmentation is a subset of them. So like set functions or segmentation, it's the same problem. It just directly starts right there. And that's all I'm pointing out. At least binary segmentation is, like if you have an objective for binary segmentation, you have a set function to optimize. I'm just pointing out by the slide, it's the same thing. So when I say set function, It's for your segmentation objective. It just means the same thing. And okay, there is that definition of submodular functions that Edmonds defined in 1970. There was no segmentation whatsoever in here, but it states something like this. So if your energy has this property, it's called submodular. Energy of the intersection of any two sets and plus the energy of the union of two sets is less than the energy of each set individually. So if that's true for any subsets, the function is called submodular. And the reason why it's important is because that's what makes it easy to optimize. Like if your energy has this property, then there is a polynomial time optimized. You can find globally optimal segmentation in polynomial time. This is a great result conceptually, and I mean, probably in machine learning people know about submodularity in general, but I'm giving you a computer vision way of thinking about it. Well, the problem is this general solver is pretty expensive. It's polynomial technically speaking, but you cannot really use this. So, but it's still a good sort of theoretical results to know where you're you want to probably deal with this type of objectives. The only question is like, what are those objectives? Why do we care about them? It's nice that they're easy to optimize, but maybe they're useless, right? So let me give you a little bit of an interpretation for submodularity. I mean, in economics, people have figured it, and by the way, submodularity is not just something we care about in vision. Like in machine learning, people use this. In economics, it's a condition that's useful all over the different application domains. But for economic people, it's very nice because submodularity is diminishing returns. If you're Trump and you're rich and you have $1 on the street, you're not gonna be as happy getting that extra dollar as someone who is poorer than you. So if you a subset of Trump, you have much less wealth, or you'll be much happier if you pick up $1 than Trump. That's diminishing returns. And for that, surprisingly, this is submodularity, and it's actually very easy to prove that this is equivalent to the previous condition. Well, but yes, I'm happy for people in economics that they have this nice interpretation. What does it mean for segmentation? I don't know. But there's another interpretation that is kind of easier to introduce in the context of simpler submodular functions. Let's consider second order submodular functions, which means that the factors I'm having there is only pairwise. So it's pairwise energy. And in this case, it's really easy to prove that submodularity is equivalent to this. So for any pair, this factor should have a property that the energy of 0, 0 plus the energy of 1, 1 should be less than the energy of the two cross labelings. And that is actually more intuitive already, because you can think of this as like the submodular function prefers similar labeling. So it's kind of smoothness or positive correlation. Actually, there is an extension of this to arbitrary submodular functions that I have on a slide later. But there's another reason I switched to, like, not only to give you this more intuitive interpretation from the segmentation point of view relevant. So it's some kind of smoothness constraint, which is useful to have often. But another practical aspect of it is actually for pairwise submodular energies, the solvers are quadratic or like low order, like you can use it with graph cuts, for example. So basically for the submodule of pairwise, it's really easy to optimize them, and this is good number. So graph cuts come from here, and this is well-known result from '68. It was popularized in computer vision community primarily by this work, but it's in principle well-known result from the '60s. So maybe I just want to make one note about the submodularity that's useful, because it may genuinely be useful for the second part of my talk as background knowledge. So you may say, okay, if submodularity it means easy to optimize, so maybe it's analogous to convexity, and in continuous explanation there is that relationship because convex functions are easy to optimize. Is that the same thing? And well, there are things to know here, is that it's not quite. And let me give you the simplest example. So take this pairwise energy, just two binary variables, x and y are 0, 1s, and alpha is negative. In this case, you can check it's submodular based on the condition I proved. Not proved, I stated. And I mean, I can visualize this function by these 4 points. So this is x, this is y, and then x could be 0 and 1, and y could be 0 and 1, right? And then I just have to tell you what this function has as a value at these 4 points. So 0, 0, 0, and then negative value, alpha. So this is my function, it's submodular, and maybe you say, well, I can extend it, right? Like if I relax it, there is a convex relaxation of this function. And indeed, yes, if you relax it that way, it's convex. You may say, oh yes, hooray, well, submodularity and convexity are similar. But it's actually easier to show that there is also concave extension it just doesn't matter. So you can extend it either way. And the message from this is not like really exactly the same thing, even though it's maybe intuitively related, at least from the point of view of optimization. But the take-home message here is like if you are going to use your discrete regularizers as loss functions in the relax setting in neural networks, for example, well, you may want to care about how you relax them, because there we use gradient descent to optimize. And if you relax it in a bad way, it may not be good for gradient descent. So the point is how you relax those regularizers may matter from the point of view how to optimize. And it resonates with some of the message in my second part, in the last part of my talk. Just a quick, maybe I'll skip the slide, but okay, I'll skip the slide. I just want to say there is an extension of this relationship between submodularity and positive correlation. So even if it doesn't have to be pairwise. Regardless of how high order is your energy, if submodularity basically means that your pairs of variables are positively correlated, even if the energy itself is not necessarily pairwise. So submodularity is positive correlation. But that seems to be useful for vision. Yes, we will typically often use that for regularization, means similarity, less noise or something like this. But nonetheless, there are lots of non-submodular energies which are useful, and a lot of research is done in the context of useful non-submodular energies and good optimizers for them, like QPBO, or there's LP relaxations, message passing, trust region methods, and all sorts of things. So it's a deep area, not deep, it's a shallow area of research, but lots of research, at least in the past. And another thing is, like, besides submodularity, you may want to say about something about high order, because high order doesn't mean necessarily you have to optimize it with a nth order polynomial solver. There are still efficient high order models, and the important thing is, like, yes, you can optimize some of the high order models well, but also it's interesting what kind of high order potentials you can be useful and you can optimize. There's also a lot of research that's been done in this area. So you can represent quite complex concepts from geometry or information theory using high order potentials, and some of them you can optimize well. So let me just give you a couple of examples of high order models. So we started from pairwise. I'm just reminding you where we were. Pairwise means you have only factors of size 2. So pairwise, like edges, smoothness on the edges. That was pairwise model, and that was low order, second order model. But for example, if you just add one more variable to your factors, click like a third order, you can already represent more interesting properties of the shape. For example, if you want to say, we want to enforce convexity of your shape. Well, you need basically for any 3 points on a line, make sure that if this point is 1 and this point is 1, then the 0 is not allowed in the middle, because that's violation of convexity. So just directly from the definition of convexity, you can say this triple clicks can work. I mean, not necessarily nearest neighbors, but like triple clicks could do this. And same for curvature. Let me just show you for curvature. So curvature, generally speaking, is a penalty for non-straightness of the boundary. I mean, you can define it in a differential geometric sense, but like generally what it stands for is you penalize non-straightness of the boundaries. And this is where your triple click of exactly the same kind as what you need for convexity, in the sense that you penalize 1, 0, 1 configuration or 0, 1, 0. Oh, actually, 0, 1, 0 is fine. Actually, yeah, 1, 0, 1 we don't want. So basically, this is a triple click that you want to discourage. You pay for it, and if you penalize those discontinuities well, the 1, 0, 1 kind of discontinuities, well, you're penalizing curvature of the boundary. And that's actually, if you go to stereo 3D shape reconstruction, curvature still gives you state-of-the-art results on benchmarks. So roughly speaking, well, the pairwise model would give you results like this. It's just representative results. I'm not making it, but if I'm not making any big point about this, except for if you go to some of the databases, the methods that are producing state-of-the-art results, many of them use curvature regularization. So it's a nice thing. We also use curvature in some of the recent projects, for example, for constructing large trees of from high resolution microscopy CT data like this. It looks easy, but it's actually a very large 3D volume. And the pixels, the vessels resolve to near capillary level. So it's actually, it looks nice from when you look at it at a distance, but when you zoom in on this data, zoo. It's a zoo. It's a very interesting optimization, well, inference problem. We have methods for solving, but we are regularizing the center line using curvature, using as an idea of continuity. Like, I mean, the standard thing like continuity criteria, connecting things, but curvature is very useful here. Yep.
And so, how does optimization work? I mean, do you have to start from is it global? So
You're talking about this?
Yes.
No, this is no. For this one, no. And for, actually...
So these are not submodular.
Yeah, actually, okay, you're right. Even this is not submodular. Yeah, I should have said that. So these are nice potentials, but they're not submodular.
And so how do you start that?
Well, we have like 3 or 4 papers using different approaches because I really was keen on curvature for a while, and I'm still interested, but sort of we know that the problem is hard. We do kind of well, but then I saw some of the results that Weikert gets with curvature, and I got kind of discouraged. So some people know how to deal with curvature better than us, I suppose.
You mean using that level set?
Don't know if well, PDEs. He's using PDEs, so he's doing quite a good job with curvature. So I it's not like I gave up, but I lost my motivation a little bit, and I went to another area where there's no Weikert. Something like this. But I mean, I still like our discrete formulation. I mean, I like it. It's just, well, you get some discrete artifacts, and with curvature, it's kind of not a good thing. Because typically when you're talking about curvature, you're looking for nice, but when your curvature is measured in some discrete sense, so you get kind of, even with pairwise regularity, we get some artifacts sometimes. You can call it Manhattan metrication. Here you can imagine the kind of metrication errors you get with this. I still like it though, because it's easy and workable. And by the way, this is with discrete model. Like, I mean, the good results, it's not like Weikert is there in a Middlebury database, but nonetheless people who take care of curvature in some way. So another model that I recently worked on, that I really like, is some kind of hierarchical inclusion-exclusion model where different labels, like you basically have an atlas. We know atlas, like the radiologists know atlas. I don't know how to represent an atlas in deep learning, not yet. But we can impose any kind of inclusion-exclusion hierarchical structure of the segments. Without any deep learning, you can get results like this. And basically, the more detailed is your model, the better results, because these segments start to help each other, even though like the complexity of the data with medical domain, first of all, is large data, but second, 3D. But second of all, the appearance is very weak. Like, I mean, they all look pretty similar. The textures, I don't know if it's discriminant. So you really have to rely on the knowledge of the structure, or the, I don't know, geometric structure, topological structure, I don't know how to call it exactly. So they start helping each other, even though the appearance-wise, many of these parts are indistinguishable. So I don't know if the deep learning will help here in any way. But nonetheless, I'm just really happy with this work, even though the postdoc who works on this, like, I mean, he did a great job, but like he wants to do deep learning now just because. Just because. Okay. Okay. Anyways, so I have just about the right time for my shallow deep part. Did you get it there? Shallow deep part. Okay. Anyway, so so we found interesting ways for kind of benefit from the prior work that in all the insights we had for the realization for shallow segmentation, how it could be useful, at least in the context of weaker supervision for deep learning segmentation. So we're basically going to use some of those energies that you've seen as loss functions. And let me just kind of give you a gist of it. So, all right, so what you start with is you have those images, and if you have full ground truths like pixel precise, then you can train your network to find features which are linearly separable to simplify segmentation. Well, I'll try to do the training based on much weaker input from the user. So instead of the full labeling, I'm just expecting the user to put seeds on some of the pixels. And well, that's what I mean by weak supervision here. And it allows me very clean entry into this domain. And some of you who know about graph cuts a little bit more, they kind of may sense that, because this is easy to see how that goes into shallow regularizers. Yes, how do we do this? Well, let me first give you a high-level semi-supervised learning, genial semi-supervised learning example that I'm sure many of you know well better than me. I'm just giving you this as a part of my story. So suppose you have some labeled examples, and there's a new example that just came in, and you have to label it. Well, you would say perhaps if you use nearest neighbor classifier, you would classify this question mark as a negative because it's closest. But if you have lots of untrained sort of examples that are in your data, but they are not labeled, well, you may change your opinion if you see this. So if your old data looks like this, then you may say, well, yeah, but it sort of seems to be kind of fitting this subspace or whatever you want to call it, and maybe you will classify it positively now. And that's basically an example of how the unlabeled data may change your opinion. We're pretty much using the same concept for the segmentation. So basically our partial input, partially labeled, are going to be partially labeled points, pixels. So it's not space of images. Within the image, we take some subset of pixels which is labeled. The rest is not. And we hypothesize that just the presence of those unlabeled pixels could be useful for training a network, if you know how to deal with them right. So a little bit of notation. So in the context of this unsupervised learning, you can think of as M, like you have data points, xi, with labels. So this is labeled data, and the indices for them go from 1 to m. Marked, M stands for marked. So from 1 to m, these are labeled. But then you also have points from index im plus 1 plus m plus u. So u unlabeled points, which don't have the label yi. So you don't know what's the true label for them. What you want to do is you want to learn labeling function that assigns a label to any point in a data set. So you want to learn this. And you want to learn it, well, from knowing all points and from knowing those which are marked. They give you additional information. So again, my notation, y is the label for points xi, but only for those points which are marked. So it's y is defined only for subset, while we want to find that function. So how do we do this in the context of the general learning? You define, let's say, loss function. First of all, on training, on those marked examples, like this is I from 1 to m, well, you have a zero infinity loss. If the labeling function gives you consistent label with what is given, then loss is zero. However, if on those marked example, the function that you're trying to learn gives you wrong answer, the penalty is infinity. So zero infinity penalty. And the way people would bring the other points through regularization part of the loss function, you can call it regularizer of the loss, or we call it altogether, this thing is a regularized loss. I think these are pretty standard terms. So how you can do this, for example, you'd bring some kind of pairwise affinities within the points, for example, distances in your feature space, and introduce some kind of objective that in general prefers labels for points which are close by, which have strong affinities, labels to match. This is your regularizer. And that's a pretty standard idea. I'm pretty sure most of you know this, but I still have to say it. Well, let's say Weston example from 2012, and I'm mentioning Weston in particular because that's what inspired us to do the same thing in the context of deep segmentation. So this is an example with digits, but only some of them are labeled. Some of them just, you know there's a digit, but you don't know what label it is. And then you can introduce, for example, some kind of pairwise affinity, well, maybe based on cross-correlation or something like that between the two patterns. Well, what we do is, first of all, in the context of segmentation, I want to make sure it's clear. I'm switching from f of xi just to this labeling function. So sp is for me the label point p. That's the same function. That's what I'm trying to, well, that's the output of my segmenter. Well, this is the kind of regularizer we use. So for any pair of points, labeled or not, on your training data set, well, I introduce some kind of affinity measure, and you can use the same affinity measures as what we were doing in shallow segmentation. Like, for example, the typical ones, affinity depends on the distance between the pixels. Well, often it's just affinities between nearest pixels, but it could be a bit more. And also similarity in their color. So if they're similar color and nearby, then affinity is high. And, well, not surprising, because that's exactly what we've been doing in shallow context. So what kind of regularizers can we use besides this? Well, I mean, actually, any of them. Like, I'm showing you pairwise, just the simplest example, and it connects well to what people have been doing in machine learning, is just for our regularizers, any shape prior that you have any constraint, structural constraint that you know about, would be incorporated directly as a regularization loss in the context of training. So let me give you two examples. Even without leaving the domain of pairwise interactions, you can have somewhat different models. And so I've been popularizing the grid regularizers where the interactions are between nearest neighbors, because this is where geometry lives. In this case, regularization can be connected to the length of the boundary and geometry. Somewhat recently, let's say in the last 10 years, people also use dense CRFs, and how many people know dense CRFs? I've heard about them. So dense CRFs been kind of popular also as regularizers. I'll talk a little bit about this later just to compare the two, but just to point out, even within pairwise, people have different ideas for how to regularize and have different motivations. But of course, you can use totally different regularizers. So now, another thing that I need to define for my weakly supervised segmentation is my loss function related to labeled input. And here I don't have to propose anything surprising, because basically I'm taking the same zero infinity loss that you've seen in a general context, and I write it slightly differently. I mean, I didn't have to, but I kind of move forward towards my notation later. So it's exactly the same thing, but what I'm doing is I'm switching from integer labels to basically simplex, which is what you do in deep learning. You switch to this probability distribution, if you like. So if you have integers here, that would correspond to corners of the simplex. But if you have relaxed values, that would be probability distribution more generally. So integer here, like if, for example, SP equals k, like label of pixel p is k, then that means this type of corner of the simplex. But notice in this case, it's exactly like if you think about the integer valued values of these distributions, then this is exactly this. If SP is 1 on the right point, then this is 0. And if SP is 0 at the point that should be 1, then it's infinity. It's just a relaxation of this. And this is cross entropy. Like, I mean, most of you who've done any of the, cross entropy is a term that I'm sure people have heard about. So I just switch from this notation to that notation, but it's just a relaxation of it, if you like. So the key point, however, is you compute this only on the seeds, on the points that you know the true labels for. And that's an important thing here. So this is my combined regularized loss. So this is what we call partial cross entropy, because in the context of fully supervised training, people use full mask, and then they sum this term of all pixels. That's all they have. They have just the sum of all points of this zero infinity loss, or cross entropy loss. For relaxed setting, it makes more sense to call it cross entropy. But we call it partial cross entropy because it's done only on the seeds that the user is given from the weak supervision. And the lack of the supervision is complemented by how the loss thinks you do on the remaining pixel based on your prior knowledge, either pairwise or high order or whatever you want. And for example, even the pairwise is what we had results for, gives you very interesting results. So I just want to juxtapose this a little bit just so that you see it's exactly as shallow segmentation energies we've seen before. So in the context of called Yuri, if you go there to 2001, so this is interactive segmentation with hard constraints on seeds. I just wrote it down in exactly this form because there we had only discrete labels. So relaxation of it is exactly cross entropy, but this is your zero infinity constraints on the seeds. So your segmentation in a shallow context, there's no learning here. So I'm just seeing, like, this is just the energy of the segmentation. There's no parameters of the network. So this is the consistency with the seed labeling of your segmentation. And this is your prior, shape prior, but we call it regularized loss, regularizer for our loss. And but what I'm pointing out is exactly the same thing, except in the context of, okay, first of all, I want to mention that people use this type of energies even in the following way for weak supervision. So you can take your weak supervision masks, like those partial input, those seeds, and generate a full mask from this just using the shallow optimizer. And then you can use that as like the output of the graph cut on this in this context as a fake ground truth. And I want to say fake because the graph cut may have made a mistake. And if you use that mask, and that's what some people do, and I have some plots to show you, is like your full training mask, you're going to overfit to mistakes made by graph cuts. If you use cross entropy on all of those points, treating pixels which are labeled and pixels which are guessed by graph cuts the same way. So that's the wrong way to go, and then we're not going to do that. Yes?
So the weights, are they learned?
No. W is, no, this is part of the loss function. So we're not learning parameters of the loss function. There's no learning here yet. This is a shallow slide.
No, just in the previous slide where you had WPQ.
Yeah, these are not, okay, call them hyperparameters, are you happy? We learn only what's producing S. So you see, like, the network produces S, and then we're going to learn the parameters of the network that produce S. This we treat as a, just like Weston, by the way.
Isn't that some notion of affinity?
Yes, it is affinity. I said we need affinity. Just like, okay, see, like the same thing I did here. Weston needs affinity, and he's not learning this, by the way. I don't know if I made it clear. He learns something else. This is just the loss function. So we don't learn parameters of the loss function. You see, like loss function is used to learn the parameters of the thing that produces the output that you measure using the loss function.
Just trying to understand what affinity means.
Oh, the same as what you use in shallow. It's exactly what you could have been using in the context of shallow segmentation. It's like what I said here. Well, I mean, you have nearby pixels. If, first of all, nearby, so it's some kind of kernel, affinity, right? A kernel based on distance, like pixels far away, you don't care. Close by, yes. And particularly if they're close by and they have similar color, like here, you don't want to draw a boundary. Out. It's exactly like, it's easier than you think, because what you're doing is exactly sort of regularization of the output, but you don't fix the output. Well, okay, I have one more slide that may help you. Because
the affinities don't change, only the labels change.
Yes, I mean, during training, of course. Yes, S changes a lot because you optimize all the parameters of the network. I have one slide just next that may help you a little bit. Because the difference is not as subtle, but it kind of helps to see my slide, I think, for this, even though it's not, like, I think you'll have an aha moment when you see it because it's pretty straightforward. So basically what you've seen here is just, I try to explain this in the context of, like, this is my loss function, but I'm not having theta here. I'm just, in this case, it's your shallow regularizer, for example, exactly as an interactive graph cut segmentation. But the only thing I need to, so I'm not gonna do this. I'm not gonna use that as just, okay, take my seeds and as a post-processing, generate the database of fully annotated ground truth images, and then try to overfit those. That some people did this, but this is a bad idea. Because you're gonna be, like, imagine using cross entropy on all labels produced by graph cuts as a kind of guessing what the ground truth is. All right, so what we're doing, and this is kind of the subtle difference, it's the same objective, but you're optimizing over theta here. Does it help? So that's the difference between the shallow regularizer and the loss function. Because now I treat this as a loss function for this. It's really a function not of S, it's a function of theta at this point. Even though it's the same objective. And I mean, that's what, if you open Benjo's book, it says so. Use, for weakly supervised training, use your shallow regularizers as regularization loss. It's kind of fairly intuitive, because that's the best you can do if you have lack of training data there. So whatever you know are good properties, and you notice that it's done softly in the sense that it's not like we generated a full mask. Do you see this difference? So here, I take this input, and for any of those images, I would use graph cuts in a shallow context. There's no network. I would generate full labeling. And imagine you treat that output of the graph cut shallow regularizer as your training, as your ground truth. Your ground truth, but there's no guarantee it's true. That's why I call it fake ground truth. So you overfit to fake, and then you use cross entropy on all of those points. You overfit to any mistakes, because cross entropy is like seeds, it's like hard constraints. So you're learning your network to produce a result exactly as what graph cuts told you, and the graph cut could be wrong. While here, instead, I'm not generating this ground truth. I'm just evaluating whatever output the network gave, and I use I use it as a soft evaluation. I don't produce fake ground truth at all.
So I wonder, could you like put an optimization layer on top of this S, so like you have a segment to predict?
I have a few words about optimization, if you give me a second. So, but I hope I didn't lose people here, because this is shallow regularizer, because you're optimizing just over S for any given image. Here, you sum those over different images, and you minimize this really, you think about this as the L of theta, because like this L of S, but then S depends on theta. So you use those loss as an objective with respect to theta. You optimize your network parameters, and W's are not part of it. You get that part? Okay. So basically, this is the difference between the objective function in the shallow sense and a loss function for training a network. I mean, in principle, it should be relatively straightforward. I'm not saying something. This is like all over the place in machine learning and for weakly supervised. Just in the context of segmentation, it took some effort to kind of figure that this is just the same thing. Because the domain is slightly different, because our training example is whole image. So we kind of, within one training example, we separate pixels as like labeled on a paper. Like once you get this, it seems like just the right thing to do. So let me just show you, well, okay, optimization. Well, first of all, for the time being, you can think of, okay, yes, you need to relax your regularizer, because if you were to apply, say, gradient descent, well, then you just get this. You need to get the gradient from the regularizer as well. It's part,
Yeah, I'm not referring to learning program.
Yes, this is learning problems. That's how you learn status. This is your gradient descent. I mean, this is your standard parts from cross entropy, and this is what regularizer gives. Yeah.
Yeah, but what you could also do is you optimizing standard for the S.
No, I'm optimizing it over. Well, okay, S is in the output. I really optimize with respect to theta.
Yeah, that's happening at learning.
Yeah, that's learning.
You put another optimize over S, so like theta gives you an initial S.
Is that a question or is?
Maybe
There is more. There's a little bit one more step. Like there is another way to optimize this, which if I have time, I can give. So I see why you're asking this, but I wasn't sure if that's how you interpret it. But yes, there is an alternative way to optimize this. Okay, but this is the most straightforward. And actually, even this straightforward does relatively well. So here's a graph that if I cover this in detail, I'm already done with my presentation. And if I have a few minutes to cover some extensions for how to optimize this better, perhaps then it would be like, but that means kind of this is essential plot. So first of all, I want to say this is like, it doesn't matter what network you use it for. So you see like kind of our block for what loss function, it doesn't matter what network you use. UNet, ResNet, I don't care. So, and this is representative. Like, I mean, we try different networks. They all pretty much give you comparable, qualitatively the same performance. So that's first. Second, so that axis shows the degree of supervision. What do I mean by this? I should have shown you a representative picture, but you've seen those scribbles, right? And one doesn't mean that it's a full mask. It's still weak supervision, but it's just, like we had some database from people who done some weak supervision before us. So you have a database where there are scribbles, and this controls how much of that scribble we use. So basically, it's half would mean we use only half of the scribble, not randomly sampled with like a strings from the end. So it's like half long scribble. So, but one doesn't mean full supervision. It's just still weak supervision, but like this is stronger supervision, this is weaker supervision. This 0 doesn't mean no supervision at all. It means 1 point. So we have 1 click, so 0 means 1 click, okay? That's why we have some results even with almost no supervision, but like it is with 1 click, you still get something. Not spectacular, but whatever. So now this is the quality, let's say, measured in terms of mean intersection of a union over whatever database, but because they're pretty much consistent in terms of what networks give you. So the lowest graph is what you get if you use graph cuts to generate fake ground truth. So basically the same seeds, but you use the graph cut in a shallow context just to use those seeds to produce a fake ground truth from which you then treat as a correct labeling and then use cross entropy to train your network on this fake ground truth. And by the way, this is what happens if, like this, I should have said this as well. So this kind of upper bound is what happens when you train the network with correct, full labeling. This kind of, the closer we are to get, the better we do. In principle, we could have gotten even better. Theoretically speaking, who knows? Like maybe this regularizer helps to improve generality and whatever, but I think we need a better regularizer for that. But nonetheless, so this is kind of the upper bound in a sense. That what happens when you really have, like if you keep adding in more seeds, all of the plots, of course, would converge there. So, okay, this is the worst plot in the graph, which is good, but like most impressive for me when I first saw this was this blue line. Because what this blue line is training where the loss function is only partial cross entropy. So what do I mean by this? I'm not using unlabeled points at all in my loss. I only look at the sort of, like think about this. So here you use labeling produced by the graph cuts as a ground truth. And the difference between this and this is you overfeed to wrong labelings produced by graph cuts. While here you can do better if you just trust what is true.
You said the other paper was already published. Did they not do that experiment?
No. This paper was before us.
No, but I'm saying.
This is our baseline.
Did they not, even when they did theirs, did they not even test that? That seems the most obvious.
Yes, but like when my students showed this to me, I'm like, but seriously. So, but this was the most amazing thing for us to discover. First of all, so from here to here, we add regularizer on top. So like the jump from partial cross entropy.
Each one's a paper.
Okay, one of them is a paper and then two are separate papers. Is that okay? By the way, there's so much work that I think it's totally justifiable. Like, to be honest, like to produce those plots, it seems like easy once it's all kind of put together. There's a lot of work, to be honest. So I see why you're laughing at it, and I kind of internally we also laugh at it, but I fully not uncomfortable with this because I know how much work went. Like a student was working just, and I mean maybe in part because we don't have as many resources in terms of GPUs and all, but just like I made it look easy, but it took us a while to understand this. So I'm kind of, it's a regurgitation of what we took a couple of years to think about. Even though I must say, when I'd like to give credit to Meng Tang, who is the first person on this list. It's his really idea to try this with regular losses. I was impressed because even though at that time when he was telling me I didn't know much about deep learning, but it took me 5 minutes to understand that this is great. Even before we had all full results and all, he goes, and they don't do this? And I mean, I hope you have the same feeling because that's obviously the right way to do it, despite of how trivial it is. And I would almost think that the machine learning people here would think it's trivial because that's what they do, except here we're doing this for segmentation. Surprisingly, the segmentation seemed less obvious for whatever reason. But anyway, so but jump from here to here is almost natural. So that, even though I'm happy that there's a jump, but that would you would expect this, right? But the relationship from here to here was quite interesting. So basically, don't try to fake it. Be true.
These other colors, the cyan, green, magenta, those are just different.
Yeah, different regularizers. So this is fake full masks, partial cross entropy only, and then these are different forms of regularization. So so first we actually started. If you know normalized cuts, our regularizer was normalized cut. The reason we thought it was a good one because it gives you balance. If you use dense errors, for example, they have shrinking bias, and we weren't sure pairwise is actually the good one. So, and then given how much time it takes to produce any of the results, we have to choose one to start from. So we started from normalized cut, and we at the time were working on kernel clustering. You may remember, we were on top of things and we knew how to do things. So somehow we thought that, because think about it, normalized cut is completely unsupervised segmentation. So it seemed like a perfect match to this because you're combining ideas from unsupervised segmentation, which is normalized cut, with whatever partial input you have. And it gives you balanced result. In fact, on the top of the picture, we're on the top of the paper, it's last year's CPR, we show the result of cherry picked, but doesn't matter. The unsupervised segmentation by normalized cut on an image with two cats, and it kind of separates the cats, knowing nothing what it did, but just based on whatever is properties of the standard kernel clustering techniques for unsupervised segmentation, just does the reasonable. It just doesn't know it's a cat. So basically, it just needs one pixel saying, "Oh, actually, that's a cat," and then there was this kind of internal intuition that's a better one. But it turned out that. With grid or dense CRFs, or actually combining the two, you get even better. But it's kind of, all of them worked reasonably well. I would imagine, though, that high order regularizers would work better, because all of those have shrinking bias, and I think that's the reason why. In principle, there's nothing that tells me that those weakly supervised cannot there is, theoretically speaking, why not? And however, I think that what happened, we did the case where we have full supervision, but still added regularizer, besides cross entropy regularizer, the performance goes down just by a bit. And I think because there's a bias there that we don't like. However, if you perhaps add a smarter regularizer, who knows, maybe you'll do better. So I like this slide. Unfortunately, I don't have time to, yes, of course. Say it one more time, the same number. First of all of these were compared exactly the same with the same scribbles, so there's no difference. If you ask this question on this slide, I'm not sure why. The seeds are like, okay, the input isn't quite exactly equal. We use some, again, standard database, and some big objects typically have slightly longer scribbles, but I don't have anything deep to say about this. They're reasonable scribbles. They're not exactly equal. And I don't know if we looked too closely into how balanced or unbalanced they are. They looked reasonable scribbles. I mean, something that you could have produced if you asked, give me scribbles, you know? We didn't control for balance and all that. Okay.
Is there a difference in the hardness of optimization?
Here we use just gradient descent. So in that sense, like, okay, you just need to relax your regularizer somehow in a reasonable way, hopefully. And then what you get here is just gradient descent. And that's actually another place. So if I have a few more minutes, I can show you a few slides. Oh, how much? I should, okay. Maybe I'll just skip that, but like for someone who wants to talk to me, I just want to mention that our most recent paper just accepted to CVPR. We talk about, okay, actually first, I want to give credit to these people. So we looked through the zoo of papers on weak supervision, and I'd like to say I'm very disappointed at what people did before us, except for this work. So this work by Lampert and Kolesnikov, they actually were trying to solve a somewhat different problem because they were trying to deal with just tag supervision. So it's even weaker than seeds in the sense that you don't even have a single click. You just have a tag. But I would like to say there is an overlap with some of the ideas, and they helped us to clear out our thoughts as well. So the main thing I want to mention about them is that they actually still go to seeds because they have some pre-processing step that from tags generates something like seeds. So the only difference is, in our case, the user generates the seeds. In their case, they have a fake seeds. After that, it kind of goes pretty much in the same way. And this is some kind of regularizer, but it's sort of a bit weird. Because, well, they take the output. So this is what you train. You train this network. This is what it produces. Then they push it through a dense CRF layer. So it has to be dense CRF, first of all. And then its output and this, they compare through loss. So first of all, in our case, there's just a loss. You don't need to do any of this. And second, we can do whatever we want. And there is a way to write this whole thing as one loss, and you're not going to like it if I write it as a loss. But nonetheless, this was the most interesting work that we've seen kind of in this context, which we kind of had to, we were inspired in some ways by this. So I'll skip that, and I'll just mention that you can do better. And basically, one of the things I want to, I'm kind of more like concluding at this point because I don't want to explain this in full detail, but it's kind of going towards this better optimization. One thing I'd like to say, those regularizers, and we learned this in a shallow context, gradient descent is not the best thing for them. And you can optimize them often much better with more advanced optimizers, for example, like graph cuts for the case of submodular price interactions. And for example, one thing I'd like to say, that one of the reasons why dense CRF often came up popular, particularly in the context of dense, in deep learning, they use it often as a block, regularization block inside the network, not as a loss, but like as a block, is because it's actually smoothest the energy. So like this example is supposed to illustrate to you, like this is your original one-dimensional image, these are edges, and this is how the energy of the segmentation that just divides the image into parts, depending on where. And I mean, this is the sparse CRF, it kind of likes this solution and this solution, while once you do the dense CRF, it smoothes it out. It's good for gradient descent, it's smoothing. So when you use this kind of dense connectivity, it's not the better energy, it's just easier energy for gradient descent. I just want to point this out. So for example, when we use that in our loss with gradient descent, it works better than gradient descent with this. But the new paper shows if you do better optimization of the loss, this is a better way to go. So basically, one of the things that's happening right now with deep learning, and that's my kind of last message, if you like, is that everybody's so into gradient descent that I think that solves everything. It might be true that the gradient descent, particularly the stochastic gradient descent, has some special powers. But I'd like to point out that when you use some of those regularizers, and many of the things people do, they fit it to what gradient descent can do well. And they train the hyperparameters based on this, which is what we've done in shallow in the 90s or 80s. You find not better energy, you find how to tweak your energy so that the simplest optimizer you use does a better job on it. And that's kind of where we are kind of back to this world, and I hope that we find better ways to do so. And I would like to wrap up here. I could have done a little bit better job explaining you some of the latest ideas, but I gave you the because that's pretty much what you were asking. I just don't want to waste everybody's time at this point. It's been a long talk. And, well, you do better. If you've been a gradient descent, if you do something else. But I'll leave it for you to read or talk to me after. So I'm pretty much done. Good to know useful objective for shallow segmentation because they're your regularizers when you don't want to have full labeling of your data set if you don't want to do this. And practically speaking, it's expensive. And particularly in medical case, like if you were to do any of this, like first of all, there's no way that you would label 3D volume to the last pixel. And if you ask 10 radiologists to do so and pay them huge amounts of money to spend their time on this, they would give you 10 different solutions. So basically, that's not the way to go. And I think that it's kind of more scalable way to go, at least in the medical context, but also we explore ideas for domain adaptation because we know that the networks overfeed to have a domain. So there's lots of room for regularizers. I mean, people know this, okay, but I'm specifically talking about the segmentation. And I'm also shocked to find that in segmentation people miss this because like in the context of optical flows or stereo, well, when people don't have the ground truth, they kind of were forced to use some standard smoothness or whatever for the consistency losses. So stereo optical flow, then you had to think about it was obvious. But for segmentation, for some reason, people miss this idea, even though I think it is also pretty straightforward. And I hope I made it look so. This is it.
Thanks, Yuri.
Okay.